In this class, we are going to discuss about the three-phase full-wave control rectifier with RLE load, continuous load current. This is the circuit diagram which consisting of 6 SCRs, T1, T3, T5, nothing but a positive group of SCR. Another name is the odd group of SCR. T2, T4, T6 are nothing but a negative group of SCR or even group of SCR. We are going to call this as a positive group of SCR means whenever the input voltage is positive, the particular device are forward bias. These are negative group of SCRs because whenever the input voltage is negative, the particular device are forward bias. Next, odd group. 1, 3, 5 are the odd numbers we are calling as a odd group of SCR. Here 2, 4, 6 are the even numbers, so we are going to call it as a even group of SCR. There is a closed path between the supply and the load only when from the positive group one device has to conduct, from the negative group one more device has to conduct. Suppose if the T1 T2 is conducting, the A is connected to the upper terminal, so C is connected to the lower terminal, so the output voltage becomes a line voltage VAC. In the same manner, the two devices are conducting, load is subjected to the line voltage. So we have taken the input voltage as a line voltage, VAB equal to Vm sin omega t, VAC equal to Vm sin omega t minus 60 degrees, VBC equal to Vml sin omega t minus 120 degrees, VBA equal to Vml sin omega t minus 180 degrees, VCA equal to Vml sin omega t minus 240 degrees, VCB equal to Vml sin omega t minus 300 degrees. In this manner, we have taken the 6 line voltages because we want to develop the output voltage waveform. To find the starting point of the sine waves means we have to make this angle equal to 0 and find the value of omega t. VAB starting point is omega t equal to 0. VAC starting point equal to omega t equal to 60 degrees. Like that, at every 60 degrees, one sine wave is starting. Now, we have taken the 6 line voltages as an input voltage. Each line voltage is displaced by 60 degrees. Here we have taken the scale 0 degree, 60 degree, 120 degree, 180 degree, 240, 300, 360 degree. Now you draw one sine wave with a starting point 0 degree, that is VAB. Now you draw one more sine wave with a starting point 60 degrees, that is VAC. Now you draw one more sine wave with a starting point 140 degrees, that is VBC, and one more sine wave with a starting point 180 degrees, VBA. Next VCA, next VCB. Now you observe here 60 to 180 degrees, 60 to 120 degrees, VAB is more positive out of remaining line voltages. Nothing but a phase A is more positive whereas the phase B is more negative in that duration. From 120 to 180 degrees, VAC is more positive. Nothing but phase A is more positive whereas the C phase is more negative. 60 to 180 degrees, phase A is more positive. So, in phase A, the T1 is connected from positive group. So, the T1 is forward bias from the 60 degrees. So, we have to apply the triggering voltage to the T1 from this point 60. Once the SCR is on means it has to conduct a 120 degrees in a 3-phase converter. Next which device is on means next T3 is on, next T5 is on. After 120 degrees of conduction of T1, T3 is on, next T5 is on. See here we have taken the 30 degrees as a firing angle. So the T1 is on at 90 degrees. It will be conducting up to 210 degrees. Next 120 degrees, T3 is conducting. Next 120 degrees, here 30, here 90, T5 has to conduct. Next one more point is the delay angle between any two successive SCRs is 60 degrees. Nothing but a T1 to T2. The delay angle between T1 to T2 is 60 degrees. So the T1 is on at this point 90 degrees. So T2 has to on at this point, that is 150 degrees. So T2 is on at this point. These are negative group of SCR. So from this point to this point, T2 is conducting. Again from the negative group, next number is the T4. So remaining 90 degrees and here 30 degrees, T4 is conducting. Here 120 degrees, T6 has to conduct. For a firing angle 30 degrees, we mention the what is the conduction of the T1, T3, T5 here, T2, T4, T6 here. Now we are going to find the region in which two devices are conducting. Suppose if we take 0 to 30 degrees, T5 and T4 is conducting. That you have to write here. From this point to this point, T5, T6 is conducting right here. Again from this instant to this instant, T1, T6 is conducting. Like that you have to complete. So every 60 degrees, two devices are conducting, one from the positive group, another from the negative group for the firing angle alpha equal 30 degrees in this waveform. Now we are going to develop the output voltage waveform. Suppose here T1, T6 is conducting. Nothing but T1, T6 is conducting. The load is connected to the A phase. T6 means B phase is connected to the lower terminal. So the output voltage becomes a VAB. In this region, you have to see how the VAB changing. You take up the same waveform to here. This is VAB. T1, T2 is conducting. Nothing but a T1 is T1, T2. The upper is connected to the A phase, the lower is connected to C phase. So VAC. So in this region, you have to see the VAC, how the VAC is changing. You take up that one waveform. Next, T3, 2. 3 is nothing but here B phase is connected here, 2 is nothing but a C phase is connected here, nothing but a VBC. So in this region, let us see how the VBC is changing. This is the VBC. In this manner it is changing from maximum to the minimum. Now we complete the remaining segments also. This is the output voltage waveform. This instant, nothing but the instant at which the T1 is on, that we can write it as a pi by 3 plus alpha. Now this instant we can write it as a nothing but 60 degrees. For this one you have to add the 60 degrees. We are getting the 2 pi by 3 plus alpha. We have taken the load current as a constant load current. So this is the constant load current, does not changes with respect to the time, which means that load is consisting a high amount of inductance. Under VB, whatever the current is there, that segment you have to write it as a ICB. Here VAB. So this current is nothing but a IAB. You mention like that. Now we are going to draw the phase A current. So ICA, nothing but the current is starting from the C phase, goes to the load and return to the A phase. So the phase A current is nothing but a negative, that is equal to the load current. So in this region, phase A is not supplying any current. So phase A current becomes 0. Here the current is starting from the phase A and return to the phase B. So the phase A current is equal to the load current, that is positive. Again here in this region also phase A current is positive. Here phase A current is 0. Here phase A current is negative. If we draw the phase A current, see from this point to this point, phase A current is positive, that is equal to load current. Here phase A is not supplying any current. So from this point to this point, phase A is supplying a negative current. Now we have to find out the average output voltage. So what are the waveform is there from this point to this point? The same waveform is repeating. This instant we are writing as a pi by 3 plus alpha, whereas this instant we are writing as a 2 pi by 3 plus alpha. This voltage is nothing but a VAB. Now we are going to integrate the VAB voltage limits from 5 by 3 plus alpha to 2 pi by 3 plus alpha. Whereas the VAB expression is the VML sin omega t. Base length becomes a 60 degrees. So the average output voltage equal to 1 by base length pi by 3 3 goes to the numerator, so 3 by pi. Limits from pi by 3 plus alpha to 2 pi by 3 plus alpha VML sin omega t d omega t. Now we complete this integration and substitute these limits. We are getting the 3 VML by 2 pi cos of pi by 3 plus alpha minus cos of 2 pi by 3 plus alpha. Now use the formula cos c minus cos d and simplify that one. So finally we are getting the 3 VML by 2 pi cos alpha. Now we are going to find out the variation of average output voltage versus firing angle. Take the firing angle on the x-axis, average voltage on the y-axis. You can change the firing angle from 0 to 100 degrees. Now we are taking the three values for the firing angle. One is 0 degree, 90 degree and 180 degree. In this expression, if we take the firing angle alpha equal to 0 degree, we are getting the 3 VML by 2 pi. That point we are getting here. If we take the 90 degrees, so this value becomes a 0. That point we are getting here. In alpha, if you take the 180 degrees, we are getting that point minus 3 VML by 2 pi. That point we are getting here. If you line join the 3 points, that gives the variation of the output voltage versus firing angle in a 3-phase fully controlled converter with a RLE load, constant load current. So from this diagram, you can say very easily that the firing angle less than the 90 degrees, the average output voltage is positive. The firing angle more than the 90 degrees, the average output voltage becomes a negative. So if you maintain the firing angle less than the 90 degrees, the converter will be acting as a rectifier. If we maintain the firing angle more than the 90 degrees, the converter will be acting as a inverter. Thank you very much for watching this video.